Hi everyone, welcome to part 3 of lecture 7. And in this lecture, we will see De Morville-Laplace normal approximation. Before giving the details of this approximation, remember that we can solve any normal random variables by using the standard normal form, right? So, and what was the standard normal form? Let's say x is normally distributed with the parameters mu is equal to 0 and sigma is equal to 1. Okay, this is the standard form of the normal distribution, standard normal distribution. And this standardizing can also be used to approximate the binomial and the Poisson random variables. Remember that the binomial can be seen as sum of independent, identically distributed Bernoulli random variables, okay? And as we will see later, the cumulative distribution function of the sum of independent, identical distributed random variables converge to a normal CDF. And that convergence will work better as n close to infinity, n times p is greater than 5, and n times 1 minus p is greater than 5, which is advised by your textbook by the Montpellier. So what that means actually, we can standardize that random variables from binomial or Poisson. We can use the standard normal table. So instead of doing long calculations, I will show you that kind of long calculations in an example. We can just use the standard normal table. It is an easy way. And this same process can be done to approximate the Poisson random variables in a same manner. So if x is a binomial random variables with parameters n and p, and don't forget the binomial random variables or binomial distribution can be some of the Bernoulli random variables, and its expected value will be n times p, and the variance will be n times p times 1 minus p. How we can standardize that kind of random variable? So remember, the standardizing process was x minus mu divided by sigma, right? So from given random variable, we will subtract the mean of them, and then we will divide that value to the standard deviation. So what is the mu in the case of binomial distribution, which is n times p, right? And what is the standard deviation, which is the square root of n times p times 1 minus p. So same thing for the Poisson random variables that has the parameter lambda and its expectation and the variance are equal to lambda. So in this case, let's say which is the standardizing way, and the mu is equal to lambda, right? And the sigma is square root of lambda. So this is how we can standardize the Poisson and binomial distribution. But before showing you how that approximation works, let me introduce you some important theorem, which is called the central limit theorem, okay? Which is CLT. Let's say there are some random variables x1, x2, x3, it goes infinity, and these are independent, identical distributed with the mean of the expected value of xi is mu, and the variance of xi is equal to sigma squared. The central limit theorem, the CLT says that Sn, which is equal to x1 plus x2 plus s3 plus xn. So we just take n of those given random variables. Then we can write Sn normally distributed with the parameters n times mu and n times sigma squared, regardless of the distribution of the individual random variables. Okay, so the first thing we need to keep in mind this term, this one. So in summary, if I am given some random variables which are independent, identically distributed, with the expected value of mu for each x and the variance of sigma squared for each x. And then if I create a new random variables such as x1 plus x2 plus x2 until xn, then I can say that Sn is normally distributed with the parameters n times mu and n times sigma squared. So let's look at how this works for the binomial distribution. Let's say xi has a binomial distribution, which is that can take two values, 0 and 1. Let's say this is success with the probability p, and let's say this is the failure with the probability of 1 minus p. So what is the expected value of x, xi? Just simply the 0 times 1 minus p plus 1 times p, right? So the expected value of x is p. And what is the variance of xi, which is, remember that the expected value of second moment minus expected value of first moment squared. So that will be the 0 squared times 1 minus p plus 1 squared times p minus p squared. So it will be, this is 0, that will be p times 1 minus p. Okay? So the variance of that x is p times 1 minus p. So what does CLT, the central limit theorem, tell us? The n of those random variables will have a normal distribution with the parameters n times mu and n times sigma squared. So I can say that if I took n of them, so Sn will be n times mu. What is mu in here? The expected value of xi, which is p, and the variance is p times 1 minus p. So I have n of them. That will be n times p times 1 minus p. Okay? So by using the central limit theorem, we can say that we can approximate that binomial distribution to the normal distribution with these parameters. Okay, so keep those in mind, and let's look at how these things make the calculations much more easy. So assume that I flip a coin, and that's not a fair coin, and with the random variables 0 and 1, let's say this is head and success, which is with the probability of 0.4, and let's say this is the failure with the probability of 0.6. Okay, and let's say I flip it 100 times. If I ask you what is the probability of x will be between, let's say, 100 and 400. Okay, So how we can calculate this one? First, x can take the values 100, 101, 102 until 400. For each of them, I have to calculate this thing, right? 500 choose 100 for this one times 0.4 times 0.4 to 100 and 0.6 to 400, right? So this is in general form, which is n to k times b to k times 1 minus p n minus k. Okay. So this is the probability of x is equal to 100, and I have to do same thing for the 101. What I mean, it will be times point. Okay, so I have to repeat this calculation for all of them, and then I have to sum all these things. So in other words, I have to do these calculations. I can equal to 100 to 500 and 500 to choose I will start from 100, and the P is 0.4 to the I, which is the required number of success, times 0.6 and 500 minus I. Okay? So this calculation takes too much time, and it is a tedious job to do that, right? But what we can do that? We can do that. Let me open a new page. What the central limit theorem tell us? It tell us the Sn, if I approximate the binomial distribution to normal distribution, I can say that the new variables will be normally distributed with the NP and n times p times 1 minus p. Okay? So this is for the binomial distribution, the approximation of the binomial distribution to the normal distribution. So what I am given, I know the number of trials, 500, and the p is 0.4. So what is MP, which is 200, and what is this one? I think that is 120, right? So what that means, that given binomial distribution, that one, the xi is equal to 0 and 1 with 0.6 and 0.4, which is a given flipping point example in our case, I can approximate that that experiment, that distribution to the normal distribution with these parameters. So, and then what I can do, I can standardize, I have to standardize the x value. So what I am asking, the probability of x that will be greater than or equal to 100 and will be less than or equal to 400. So let's standardize this one. Okay, so that will be the 100 minus mu, and the mu is 200 in this case, divided by sigma, which is the square root of 120. And same thing for this one. And also same thing for this one, which is so this is a number A, and this is a Z. Remember the standard normal distribution, we have used Z. And this is the sum value, right? B. So remember the table, this standard normal table. How can I calculate this probability? This probability is actually the phi B minus phi A, right? So I will just look at these values at the table and I will get the values. I mean, let's say this is 0.5 and let's say this is 0.3, then I will end up with 0.2. So what that means, I can say that the probability of x will be greater than or equal to 100 and will be less than or equal to 400 is 0.2. So instead of where is it? Instead of doing all this calculation, what we did first, thanks to central limit theorem, we approximate this binomial distribution to the normal distribution with this way, and then we have standardized this normal distribution to be able to use this standard normal table, and then we just put the values or look at the values from the table, and we just make a simple calculation. Okay. So we have seen that how we can approximate the binomial distribution to the normal distribution thanks to central limit theorem, and then we've seen that how we can standardize that normal distribution to solve much more complex problems in an easy way. However, the binomial and the Poisson are discrete random variables. That's why a continuity correction increases the quality of the approximation. And let me explain what I mean by saying the continuity correction. So let's say I'm going to approximate the binomial distribution to the normal distribution, okay? And in this graph, that rectangle corresponds to PDF of some random variables from in a binomial distribution. So the main logic behind the approximation is actually using some rectangulars to calculate the area between some range. What I mean, let's say I have 2 points, K and L, and I'm asking to probability of X will be greater than or equal to K and will be less than or equal to L. So what I can do, if this is continuous, it's easy, just I can calculate all this area. But if it is discrete, and if I approximate it, what I mean, I will fill all this area with some tiny rectangles, okay? Like that. And at the end, sum of the area of all these rectangles will give the area of this region. Okay, this is the basic logic behind the approximation. But at the exact point on the K, there will not be a rectangle, right? That will be a line like that. That means I cannot calculate the area at this point. So to increase the approximation of the quality of the approximation, to improve the quality of the approximation, what I can do, instead of calculating this one, I can calculate the K minus some epsilon value, X, and L plus some epsilon value. So what I mean, actually, I will add some numbers, and I will increase that area a little bit, okay? And this epsilon is usually 0.5 or 0.05. So if I calculate the area of this new region, that will cover the points K and L for sure. Okay, so the idea is the calculating the probability X is equal to K. I cannot calculate the area of rectangular at that point. That's why I can create a rectangular. Okay, so let's say this is the point K and that is the line, because that should be line because I'm asked to X will be equal to K, but I cannot calculate the area of that one. So what I can do, what did I do? I just created a tiny rectangular, okay? Something like that. So in this case, I am sure that this rectangular will cover the point K. So this is the main logic. So by using this one, I can generalize that rule for the range case. What I mean, if I'm asked the probability of X will be greater than or equal to K and will be less than or equal to L, I can just subtract some values from the K and I can add some small values from the L, and that will provide a better approximation. Okay, so this is the continuity correction. Well, this is the end of lecture 7, and thanks for watching.